physicists, today we're going to have a crack at going through what I think are the most important parts of AQA GCSE paper 1. So we're going to start with topic 1, energy, and we're going to jump straight in with the conservation of energy. It's not asked as definition every year, but every year there will be a question on conservation of energy. So it is worth knowing. So the conservation of energy states that energy cannot be created or destroyed only transferred from one store to another. So there's a finite amount of energy in the universe. We're not going to get any more. We can't make any more, but equally we can't get rid of it. There's like a limit on the amount of energy that we can possibly have in the whole universe, and we're just transferring it from one store to another. So there are 8 energy stores. You don't need to be able to recite them, but you need to know what each of them does. So there's never going to be a question that's like list all 8 energy stores, but there might be a question that's like, you got a hot cup of tea, what energy store has it got? And that would be thermal energy, because thermal energy is stored in hot objects. The hotter the object, the more thermal energy it is storing. Next up, we've got chemical energy, and this is energy that needs a chemical reaction to release it. Really common examples are cells when we get to circuits, and also food. Right, kinetic energy is energy that's stored in moving objects. The faster an object is moving or the heavier an object it is, the more kinetic energy it will be storing. There's an equation for kinetic energy we're going to go through in just a minute. Next up, we've got gravitational potential energy, always called gravitational potential energy, not just gravitational energy. And this is energy that's stored in objects above the Earth's surface. So for example, my pen, if I hold my pen up, it's storing gravitational potential energy. We call it potential energy because at the moment it's just storing the energy. It doesn't actually do anything until I let go. So it's got the potential to do something. So that's why we call it gravitational potential energy. Next up is elastic potential energy, which is the energy stored in objects that are stretched or squashed. So objects that are stretched or squashed, like a spring, something like that, or an elastic band. When we stretch it, we're storing energy. When we let go, that energy will be transferred to a different store, normally kinetic energy. Right, electrostatic is energy that's stored between charged objects. So objects that are positive and negative, like protons and electrons. So we know that protons and electrons will attract towards each other if we have them close enough to each other. And so they're storing energy by being charged. Now, next up, we've got nuclear energy. We're not asked a lot about nuclear energy. You just need to know that it's the energy that's stored in the nucleus of an atom, and that's about it. There's a little bit on nuclear fission, nuclear fusion if you do triple in topic 4, but for topic 1, if you're doing combined, that's all you need to know. And then finally, we've got magnetic energy, which is the energy stored between magnetic objects. So stored between magnetic object. So you need to be able to look at an example that the exam might give you and work out what type of energy store it has got. It's normally pretty obvious in the exam. They normally do make it really obvious. So go with your first instincts with these ones. Right, so there are 3 types of energy that you need to know the equation for. The first one is kinetic energy, and the equation is kinetic energy is equal to half multiplied by the mass of the object multiplied by the velocity squared of the object. Now, kinetic energy, because it's an energy, we measure it in joules. Mass is measured in kilograms, and velocity is measured in meters per second. So let's say that I've got a ball that's got a mass of 3 kilograms and a velocity of 2 meters per second, and I want to work out its kinetic energy. So the kinetic energy is equal to a half multiplied by the mass, which is 3, multiplied by the velocity, which is 2. But as you can see here in the equation, the velocity is squared. So I'm going to square that velocity. So that 2 is squared. It's only the 2 I'm going to square. I'm not going to square the rest of it. I'm only squaring that 2. So this would be the same as saying a half times 3, which is 1.5, multiplied by 2 squared, which is 4. So 1.5 times 4 would be 6 joules. So that's how we use our kinetic energy equation. Now, the gravitational potential energy equation is this one here. So EP, so gravitational potential energy, is equal to the mass multiplied by the gravitational field strength on Earth multiplied by the height of the object. So because it's energy, it's measured in joules, obviously. Mass is measured in kilograms. Gravitational field strength is newtons per kilogram or meters per second squared, because it is an acceleration as well, but you can use whichever unit you want. I use meters per kilogram. And height is measured in meters. Now, you need to know that G on Earth is 9.8 newtons per kilogram. You are expected to remember that in your exam and use it when it needs using, okay? So let's imagine that we've got an apple that's being held in a tree 3 meters above the Earth's surface. So the mass of the apple, let's say, is 500 grams. And the height is 3 meters above the Earth's surface, and we want to work out the gravitational potential energy. Now, because mass is always in kilograms, not grams, the first thing I'm going to have to do is divide my mass by 1,000 to get 0.5 kilograms. So 0.5 multiplied by the gravitational field strength on Earth, which is 9.8, multiplied by 3. I'm then going to pop all those numbers into my calculator. You want a calculator like this. It's really, really important that you get a good calculator, okay? You want one of these Casio ones that's got a fraction button on it and can also do standard form and things like that for you, because it's super, super helpful. So we're going to do 0.5 times by 9.8 times by 3, which gives us an answer of 14.7 joules. Now, the final equation we're going to have a look at is this one over here for elastic potential energy, okay? So elastic potential energy is the energy that's stored in anything that is stretched or squashed. So normally we're thinking about a spring or an elastic band. And it's the elastic potential energy is equal to a half kx squared. It's not, it's half ke squared, sorry. And so you can actually see it's very similar to the equation for kinetic energy. We've got the half, we've got something, and we've got something that's squared. So this is our elastic potential energy, so it's measured in joules. This guy here is spring constant, okay? So that tells us about how easy or difficult it is to stretch a spring. If it's really easy to stretch a spring, we say it's got a low spring constant. If it's really difficult to stretch a spring, we say it's got a high spring constant. And that is measured in newtons per meter. And then this E here stands for extension. It's not length of a spring, it's the extension of a spring. And it's got a unit of meters, okay? So this is extension. So let me talk you through what we mean by extension. So we're going to imagine that we've got a spring, and let's say that it's 5 centimeters long, and I stretch it so that it's now 10 centimeters long. The extension would be the difference between the numbers. So it'd be 10 take away 5, which would give me an answer of 5 centimeters. Now, because the extension needs to be in meters, we need to convert the extension into meters before we can use it in an equation. So we divide by 100, and that would become 0.05 meters, okay? So that's what our extension would be in meters. Let's say this spring has got a spring constant of 100 newtons per meter. We could then work out the elastic potential energy stored in it when it is stretched. We do a half multiplied by the spring constant, which is 100, multiplied by the extension, and it's just the extension that I'm going to square, because look at my equation. Your equation is a bit like the instructions that tell you what you need to do. So if you look at that equation up there, it tells me that the extension is the only bit that I need to square. So I could do the half times 100 first. That'd be 50 multiplied by 0.05 squared. I'm going to use my calculator for that. That gives me an answer of 0.0025. And then I can multiply these guys together to get an answer of 0.125 joules. So that's how much energy would be being stored in my spring. So that's how we use our three basic equations for energy: kinetic energy, gravitational potential energy, and elastic potential energy. Now, the final bit about energy that comes up quite a lot is about energy resources, okay? So how do we make electricity? And what you need to know about them is, do they produce CO2? Are they renewable? And what are the environmental issues with them? So we're going to start with fossil fuels. Now, fossil fuels are our coal, oil, and gas. We burn them to produce heat. We use that heat to heat up water, turns it into steam, and it turns a turbine. Now, one of the big problems with fossil fuels is that when we burn them, they release greenhouse gases, including carbon dioxide. If you're ever asked about an environmental issue with burning fossil fuels, don't just say greenhouse gases. Be specific. Make sure you're going to say carbon dioxide or nitrous oxide or water vapor. Be specific. Okay. So yes, fossil fuels do produce carbon dioxide. They're also non-renewable, which means that we cannot replenish them quickly or easily. The main environmental issue is that carbon dioxide contributes to the greenhouse gases that cause global warming. Okay, so that's why the greenhouse gases are an issue, is because they cause global warming. Just make sure that we're specific and we can collect as many of those marks as it's possible to get in your exam. So when you're talking about carbon dioxide, you want to link it to being a greenhouse gas, and you want to link that to global warming. Right, next up, we've got nuclear. So this is a really common misconception, because nuclear, when it's actually the fuel itself producing electricity, does not produce carbon dioxide. However, it's also not renewable. We normally use uranium as our nuclear fuel, and once we've used it, we're not getting any more of it because it's formed by supernovas. It's formed by dying stars. We're not getting any more of it. So this is a really common misconception. Students think that just because something doesn't produce CO2, then it must be renewable. It's not true. Nuclear doesn't produce CO2, but also isn't renewable. The main environmental issue with nuclear power plants are that we get radioactive waste. And that can be really harmful to the environment. We have to find something to do with it. We normally bury it deep underwater or deep underground. But we have to find something to do with this radioactive waste. We could also say that nuclear power plants cost a lot of money, and they also have a very long decommissioning time. It takes a long time to decommission them. Right, next up is biofuel. So biofuel is fuel that's produced from decomposing animal matter and carcasses and plant matter and feces and all that good stuff. So anything biological, we put it in a big old tank, we let it rot down, and it produces this fuel that we can use for combustion. Okay, but because it's still combustion, it still does produce carbon dioxide. However, it is also renewable because it doesn't take very long for all this stuff to break down to produce a fuel that we can use. Now, environmental issues with biofuel include the fact that it still produces carbon dioxide, which contributes to global warming, but also that it takes an enormous amount of land to grow enough crops for biofuel. So it takes up large amounts of land that we might want for food production or something like that. Next up, we've got hydroelectrics. That's when we use falling water to spin turbines. We normally hold this water behind a dam. Doesn't produce carbon dioxide, and it is renewable. But the big issue with it is that it means that we normally have to flood large areas of land, which is bad for habitats, but also it means that we've got less available land for growing food, we've got less places to live, etc., etc. Right, wind. Wind is using those big old turbines that we might have seen. The wind blows the turbines, and inside the turbine, it's inside like the house on the top, it's going to spin a generator. So they don't produce CO2. They are renewable, but they're an eyesore. They're noisy, and they kill birds. Right, solar is next. So this is using the solar energy that we get from the sun and converting it into electricity using solar cells. You might have seen solar panels on the top of like someone's house. That is solar. Okay, so they don't produce carbon dioxide, and yes, it is a renewable energy resource, but there are several issues with it, mainly that it takes up a lot of land. If we wanted to have enough solar panels to power the UK, we'd need to solar panel over a huge amount of land, okay? So they need a large area. And then the problem is that we only can make electricity whilst the sun is shining. We live in the UK, the sun doesn't shine that much, they're quite unreliable. Same with wind. With wind, we've got to wait for the wind to blow again before we can make electricity. So wind and solar are both quite unreliable. Right, next up, we have got tidal. So tidal, again, doesn't produce CO2 and is renewable. So it's when we put turbines like in some sort of tidal flow, normally in rivers. So for example, like the Thames has a tide. So it has a high tide and a low tide, and the water goes in and out on a really regular basis. So it is quite reliable because we know the regularity of it. But the problem is that it can disrupt the wildlife because fish can get caught in it, stuff like that. Tidal can also be very expensive. And then finally, we've got wave power. So wave is when we're putting generators in the sea and using the waves to turn the turbines. Again, it doesn't produce CO2 and it is renewable. However, again, it can harm aquatic habitats. So it can harm the habitats of any of those creatures that are living in the sea. So that is a really quick run through on what I think are the most important points of topic 1 for you. Coming up next is electricity. Next up is topic 2, which is electricity. So we're going to do series and parallel circuits to start with. So in a series circuit, we've only got one pathway for current to flow down. So just like I've drawn here, that all we've got is we've got one way for the current to flow. So remember that this is a cell. Now, the long side of the cell is positive, the short side is negative. I always think about it as, do you want a long chocolate bar or a short chocolate bar? Of course, you want a long chocolate bar, so the long chocolate bar is positive. So current always flows from the positive terminal to the negative terminal. Now, the thing is that current is like how fast the charge is flowing in this circuit. Because all of the electrons are just following each other around, then that means that whatever the current is here, let's say that the current is 3 amps here, it's going to be the same here. It's going to be the same here. So the current is the same everywhere in a series circuit. Is the same everywhere. Now, potential difference, on the other hand, is a little bit different. So potential difference is the difference in the electron's energy from one side of a component to the other side of the component. Potential is just a physics word for energy. Difference, well, what's the difference between one side and the other side? So let's say that the potential difference over my cell is 3 volts. That means that I'm giving each coulomb of charge 3 joules of energy. And you can kind of imagine it as like a little electron carrying a ball of energy. Okay? Now, what's going to happen is that because there are 2 bulbs in the circuit, it's not like one of the bulbs is going to turn on and the other one's not going to turn on. So what the electrons will do is that they will share their energy. They'll transfer some energy to this light bulb, some energy to this light bulb. if the light bulbs are identical, they'll transfer 1.5 volts of energy to that one and 1.5 volts of energy to that one. Okay. If the light bulbs aren't identical, let's say that this one is really small, so it's got a smaller resistance, which is like the opposition to the flow of charge, then that might split to being 1 volt and 2 volts. But it's still all got to add up to 3 volts. The electrons have got to get rid of all their energy as they go through this circuit. They've got to have given away all their energy. So we say that the potential difference is split across the components in a circuit. So let's talk about parallel circuits now, because in parallel circuits, we've got multiple pathways for my electrons to go down. So here, I've just got 2 bulbs again, but they are now in parallel. So my electrons can either go this way, or they can go that way. There are 2 possible pathways for them to go down. A really common misconception that students have, though, is that some electrons can magically go through both. No. Don't forget that a circuit has got to be a completed loop from one side of the cell to the other side of the cell. So the electrons are always going to move in a circle from one side of the cell to the other side of the cell. So they're either going to go through one bulb or they're going to go through the second bulb. They're not going to go through both. So let's talk about how that affects the current then. Because again, current is the rate of flow of charge. But the charge is splitting here at this junction. So if the current here was, let's say, 4 amps, then the current would split at this junction. If these bulbs were identical, so they had the same resistance, we'd get 2 amps here and 2 amps here. So 2 and 2 still add up to make 4. Here is another junction. The current's going to recombine again here. So therefore, we have a current of 4 amps again there. Now, if these bulbs didn't have the same resistance, or if they were different components, let's say this is now a resistor, then this might well change. This might now become 1 amp, but that would mean that this one would now become 3 amps. They've still got to add together to make 4. Now, potential difference is a little bit different in a parallel circuit to in a series circuit. Because if I've got a potential difference of, let's say I've got a potential difference of 10 volts over this cell here, well, hang on, the electrons, that means they're carrying 10 joules of energy per coulomb. And what that means is that the electrons that go this way will transfer all their energy to this resistor. The electrons that go this way will transfer all their energy to this bulb, because there's nothing else in that pathway. So what it actually means is that the potential difference over each component in a parallel circuit is the same as the potential difference over the cell. Now, this is only true, though, if I've only got one component in this branch. If I had 2 cells in this branch, 2 bulbs in this branch, then we'd go back to having our rules again in series. So, for example, for this one, it might be 5 volts over this one, and if the bulbs are identical, another 5 volts over that one there, like that. So in a parallel circuit, we say that the current splits, but the potential difference is the same across each branch. That's what we call these guys here. We call them branches. Right. So let's talk about our required practicals then, because there are 2 that you need to know for electricity. Your first one is about the resistance of a length of wire. Something like that, okay? So this is your wire here, and you're holding it with some crocodile clips. And what you're going to do is you're going to change the length of the wire, because what that's going to do is it's going to change the resistance. Resistance is the opposition to the flow of charge. So if we imagine that we can look inside a wire, Now, we all know from chemistry that we've got delocalized electrons in a metal. That's what makes them such good conductors of electricity. They've got these delocalized electrons floating about in a sea of ions. So let's imagine my electron here. Now, electrons have got a negative charge. So if I apply a potential difference across them, that means that one end of the wire will be positive and the other end of the wire will be negative. So because electrons have got a negative charge, they'll be repelled away from the negative and attracted to the positive. So we're going to have lots of electrons flowing through this wire. But as you can see, my big old ion is getting in the way. So those electrons are going to collide with the ion and transfer some energy. That is what causes resistance, okay? It's that causes resistance, and we can work out the resistance from the equation V is equal to I multiplied by R, where V is potential difference, I is current, and R is the resistance. Now, there's no such thing as a resistometer, so it makes measuring resistance of a component a little bit tricky. Because what we've now got to do is we've got to measure the potential difference using a voltmeter, measure the current using an ammeter, and work out the resistance from there. Now, an ammeter should always go in series, so next to the component that we are interested in, just like that. We can then pop the voltmeter across like this, and then we're going to change the length of the wire and record the potential difference and the current in this circuit. So we change the length of the wire, that will change the resistance, record the potential difference, record the current, happy days. Okay? Now, because it's an electrical circuit, it can get hot, because when these electrons collide with the ions and they transfer energy, they transfer a little bit of thermal energy. They make those ions vibrate. As those ions vibrate more and more, they get in the way of the path of more electrons. So that can actually increase the resistance. So what we want to do is we want to stop this circuit from getting hot. And a way that we can do that is that we can pop a switch in here, and we can just make sure that we turn our circuit off in between every reading. Then we can use the equation R is equal to V divided by I. So resistance is equal to potential difference divided by current. We can use that to find the resistance of this wire. So remember that this is a voltmeter, which we use to measure potential difference. This is an ammeter, and we use it to measure the current. Okay? Now, the other required practical you need to know is about how to find the IV graphs over 3 different components. You've got your diode, you've got your fixed resistor, and you've also got a filament bulb. Okay, so what you do there is you set up a circuit with an ammeter to measure current, to measure I. You set up your component here. We'll just use the resistor. But if you're doing the filament bulb or the diode, you just put that here. Set up your voltmeter across it, and then you want some way of varying the current in this circuit. You can do it using a variable resistor, or you can do it by using a variable power supply, or you can change the number of cells in your circuit. It doesn't matter, but I think for an exam, the easy way to talk about it is the variable resistor. So you change the resistance of the variable resistor, that will change the current and the potential difference, and you record those readings for a fixed resistor, a filament bulb, or a diode. Now, the trick that most students miss when talking about this required practical is that they forget that when we draw the graphs, we don't just draw the positive side of the graph like this for a filament bulb. We also draw the negative side down here as well. So what you need to do is after you've taken, let's say, 6 readings with the cell in one direction, you then switch the polarity of the cell so you can take your readings in the other direction. Now, the characteristic IV graph of a filament bulb looks like this. So you can see here that we've got a bit of a curve going on. That's because the filament bulb at higher potential difference starts to get hot and the resistance starts to increase, okay? We've also got a fixed resistor, which should work as an ohmic conductor. An ohmic conductor means it obeys Ohm's law, which is that current is directly proportional to potential difference at a constant temperature, we can tell that this fixed resistor is directly proportional, that the current is directly proportional to potential difference because it's a straight line that goes through the origin. The final component that you need to know about is a diode. Now, a diode will only allow current to flow in one direction. So it looks, I'm going to do it in a different color so it's easier to see on the axis. So it looks a little bit like that. Now, make sure, please, that you don't start going up at the origin. It goes a little way past the origin, then it goes up. So that means that if I have the potential difference one direction, no current will flow. If I turn it round, so I've got potential difference the other direction, current will start flowing. So a diode will only allow current to flow in one direction. And you need to know those three characteristic graphs. They're very important. Okay, now the final thing we're going to talk about a little bit is a little bit of household electricity. So there are 3 wires in a plug that you need to know about. We've got our live wire, we've got our earth wire, and we've got our neutral wire. So your live wire has got a potential difference of 230 volts. And it is brown, because if you hold on to it, think about what will happen, okay? Your earth wire is a safety feature. It's got a potential difference of 0 volts, and it's got a yellow and green stripe. Your neutral is also at 0 volts, and it is blue. So these are the 3 wires that you find in a plug. Now, also connected to your live wire, is a fuse. Now, the role of a fuse is it melts if too much current passes through it, and that breaks the circuit. Because the role of the live wire is to carry the current from the power station to your house. The role of the neutral wire is to carry the current back to the power station, because we know that for electricity to run, we've got to have a complete circuit. The role of the earth wire is only to do something if there is an issue. So what happens is, let's imagine that you've got like a metal toaster, okay? And in your metal toaster, you've got your live wire, which should be brown, but I haven't got a brown, so I'm going to use purple. Goes into a heating element. You've got your neutral wire that takes the current back to the power station. And we're going to imagine it's a fancy metal toaster, and so it's got a metal casing. Now, what happens is that the earth wire is only connected to the metal casing on the outside of the toaster, and then goes straight into the ground outside your house. Now, what this means is that if there becomes a fault with your live wire, if it breaks and touches the casing, then what's going to happen is that the current can flow through the casing and straight down the earth wire, okay? What that will do is it will give you a really high current, because there's going to be a really low resistance through the metal casing, give you a really high current, so the fuse will melt. That'll break the circuit and you can't use your toaster. Well, what good is that? Why do you want your toaster to break? Because what's actually going to happen if you didn't have this earth wire is that if you came along and touched that toaster, you are a lovely connection for the current to flow straight down to the earth, because you're about 90% water. So the current will very happily flow straight through you and give you an electric shock. So this is the main role of our earth wire, is it prevents us getting electric shocks off of metal appliances. Because if we've got the earth wire connected, instead of going through us, the current will always take the path of lowest resistance. So we make sure that the earth wire is a low resistance wire. The current will go straight through the metal casing, straight down the earth wire to the earth. Happy days. But then suddenly there'll be a really low resistance, so a really high current, so our fuse will melt. Now, we have also got a different type of safety feature in our houses. Now, if you've ever seen like your fuse box in your house, you'd be like, but hang on, It doesn't melt, it's just a switch and you flick it back up. Absolutely. And that is what's called a circuit breaker. So these are like bigger fuses that can control whole rooms. And the main advantage of them is that they are quicker and also that they don't have to be replaced. They can just be reset. So another thing that does the same job as a fuse, so it trips if too much current goes through it, is a circuit breaker. And there you go. That's topic 2. Topic 3 coming up. Okay, before we start topic 3, I want to tell you about this website that Brooke and I have written called MyResources. It's got all your notes, it's got videos, it's got loads of questions, it's got everything you need to absolutely boss your GCSEs, okay? So if you want to check it out, it's MyResources on the MyEdSpace website. Now, as a thank you for getting this far in the video, if you check out the description of this video, you're actually going to find a link to some flashcards for you all about paper 1 GCSEs. A little thank you for getting this far. So let's jump into topic 3 then, shall we? So we're going to start with density. Now, density is about the amount of mass an object has per unit volume. And so it's mass divided by volume. This letter here is a rho. It's a Greek letter, and that's density. Now, density can be measured in 2 different units. It can either be measured in kilograms per meter cubed, if mass is in kilograms, or if the volume is in meters cubed. But sometimes we actually measure density in grams per centimeter cubed. That's when the mass is in grams and the volume is in centimeters cubed. So just make sure that you check what unit you need to give your answer to when you are doing an exam question. Right, so there is a required practical for density. You have to know how to measure the volume of 3 different types of objects: a regular object, an irregular object, and a liquid. So we're going to start with the regular object. So you measure the mass on a balance, and then you calculate the volume by measuring the length, the width, and the height of the object. And then you multiply them together. So the length times the width times the height. You get the mass from a balance. And you can use density is equal to mass divided by volume. Happy days. Right. But if you've got an irregularly shaped object, you can't work out the volume by measuring it. You have to use what's sometimes called the displacement method, where you have to submerge the object in water. Now, there's 2 different ways of doing this. You can either use a displacement can or you can use a measuring cylinder, but the idea is the same. I'm going to talk it through using a displacement can. Some of you might have used a Eureka can before, but I'm going to call it a displacement can. So what you do is you fill your displacement can up with water until it's just below the spout. Then when you add an object, let's say that I tie a stone to a piece of string and lower it in, the water level goes up and it's going to start pouring out this spout here. So what you do is you pop a measuring cylinder underneath and you collect the displaced water. And the volume of the displaced water is equal to the volume of the object. Now, I've read hundreds of student responses where they've answered this question really nicely. They've talked about measuring the mass of the stone with a balance. They've talked about the Eureka can, how to set up the water. They've talked about how to collect the water, but then they haven't actually related it to what it is. Why do I care about collecting this water? It's because that gives me the volume of the object. So if this was a stone, that would give me the volume of the stone. Then again, I can measure the mass using a balance, and then I'd use the equation density is equal to mass divided by volume. Now, the final thing you have to be able to do is you have to be able to find the density of a liquid, and that is actually quite easy, but there's a trick. And the trick is that when you measure the mass of the water, or the liquid rather, like whatever liquid you're using, just make sure, because if you imagine that you've got a scale here, and so you're going to get your number here, right? Now, the thing is that if you put a measuring cylinder on it that's already filled with a liquid, then what you're going to get is you're going to get the mass of the measuring cylinder and the mass of the liquid. So there are 2 ways to do this. You either put the empty measuring cylinder onto your balance, tear it, and then fill it with a liquid, or you measure the mass of the empty measuring cylinder first, Then add your liquid, measure the mass of both, and then take the mass of the empty measuring cylinder away, because we just want the mass of the liquid. And then if you use a measuring cylinder, you can read the volume straight off the measuring cylinder. You've got the mass, and again, you're going to use density is equal to mass divided by volume. So there are 3 parts that's required practical, but actually, if you think it through, it's quite simple. So it's a good way to get some nice marks. Now, the next thing that I think is really important is talk about particle motion in gases. So you should know your basic states of matter. That solids, we've got those particles that are in quite a fixed position. They're just kind of vibrating in place. There's a very regular arrangement. In liquid, we've broken some of those forces in between the particles. They're a little bit less tightly bound. They can flow over each other. They take the shape of their container. But in a gas, we've got particles moving completely randomly. So if they're in a container like this, they're going to be moving randomly, and they're going to collide with the container wall. And that causes a gas pressure. So the pressure comes from particle collisions with the container wall. Okay. Now, you need to know about the link between pressure and temperature, and this comes up quite a lot. So as we increase the temperature of this gas, we know that the kinetic energy of the particles is going to increase. So as the temperature increases, the kinetic energy of those particles is also increasing. So that means that the speed of the particles is increasing. Now, because the speed of the particles is increasing, it means we're going to have more forceful and more frequent collisions between the particles and the container wall. And this is going to increase the gas pressure. When you're talking about gas pressure, you want to be talking about forceful and frequent collisions. It's not enough just to say more collisions. You need to say more frequent collisions. That is a really, really important point. Okay, now if you ask this question the other way, so about a decrease in temperature, then that means that the kinetic energy goes down, so the speed or the velocity of the particles decreases. So we're going to have less frequent, less forceful collisions between the particles and the container wall, so the gas pressure will decrease. But if you're asked about gas pressure and temperature, that is the way you're going to talk about it. Okay, the final thing we need to talk about for topic 3 is specific latent heat and specific heat capacity. There are specific definitions you need to know, so let's just make sure we've got them down. So specific latent heat is the energy required to change the state of 1 kilogram of a substance without changing the temperature. Okay, so if we're ever talking about the energy that we need to change the state of something, we're talking about specific latent heat. Now, there are 2 different types of specific latent heat. There's the specific latent heat of fusion, which is going from a solid to a liquid, and there's the specific latent heat of vaporization, which would be going from a liquid to a gas. Now, there's an equation for this, and I always remember which way around the specific latent heat and specific heat capacity are from the equations, because the equation of specific latent heat is this one here. E is equal to mL, where E is the energy transferred, that's joules, M is the mass in kilograms, and L is the specific latent heat in joules per kilogram. Now, this equation hasn't got change in temperature in it. So I remember then specific latent heat isn't the one about change in temperature, because there isn't change in temperature in the equation. So the way that we use this equation, let's imagine that we've got 500 grams of water, and I want to know how much energy I need to turn that from water into steam. Now, the specific latent heat of water is about 334,000 joules per kilogram. So here we go. We'd do E is equal to the mass. Now, this is in grams, so I need to convert it to kilograms. So I'll divide that by 1,000, give me 0.5 kilograms, multiplied by 334,000. So therefore, the amount of energy that I'd need to turn 500 grams of water into steam would be 167,000 joules. Okay, so that's the energy required to turn water into steam. It would also be the energy released if I turned steam back into water. Okay, so the energy required to turn a substance from, let's say, like a liquid into a gas is the same amount of energy that will be released when we do it the other way around. Now, specific heat capacity has got a slightly different definition. It's still the energy required, but it's the energy required to raise the temperature of 1 kilogram of a substance by 1 degree C. Okay, now be specific. 1 kilogram of substance by 1 degree C. You're not going to get your marks unless you say exactly that. So the equation for this one is E is equal to mc delta theta. E is energy, so we go measure it in joules. M is mass in kilograms. C is your specific heat capacity. That is measured in the unit of joules per kilogram degrees C. And delta theta is your change in temperature. That's in degrees C. Now, it's change in temperature. That delta means change in, you might have seen when I'm doing gradient, like delta Y means change in Y. So delta theta means change in temperature. Okay. Now, because this is the change in temperature, we're not interested in like what the starting temperature is or what the ending temperature is. We're interested in what the change in temperature is. So let's imagine that we're heating, let's say 200 grams of water. The specific heat capacity of water is 4,200 joules per kilogram degrees C. And let's say we're heating it from 20 degrees to 80 degrees. So this might be in a kettle. Okay. So we'd use the equation energy is equal to mass. Again, we're going to divide this by 1,000 to turn it into kilograms. That'd be 0.2 kilograms. 0.2 multiplied by 4,200 multiplied by, now I want to find the change in temperature because that's the thing I'm interested in. So I'll do 80, take away 20, which would be 60 degrees. So 60 degrees C would be my change in temperature. So I'm going to put 60 here because it's the change in temperature. Right, pop all those numbers into a calculator and I get an answer of 50,400 joules. And there we go. That's how we use our specific latent heat and our specific heat capacity equations. Right, final part of paper 1, topic 4, radioactivity coming up. Right, topic 4. So the biggest problem that we see with topic 4 is that students don't know squat about the different types of radiation. Okay, so if that's you, listen up and listen really closely. This table we're going to go through right now, you need to know. Okay, so we're going to start with our 4 basic types of radiation. We've got alpha, we've got beta, we've got gamma, and we've got neutron. Okay, so an alpha particle is made up of 2 protons and 2 neutrons. It's sometimes called a helium nucleus, not a helium atom, a helium nucleus, because it's got no electrons. Because it's got 2 protons, it's got a charge of +2, and 2 protons and 2 neutrons means it's got a mass of 4. Now, the penetration is like how much stuff can it go through. Now, alpha is really lowly penetrated. It's got a really low penetration. It's stopped by paper. Now, that's because it's got a really high ionization. Alpha, because it's got the biggest mass and the biggest charge, finds it easiest to ionize other atoms. Ionizing means taking electrons from those other atoms, okay? Now, sometimes we equate ionization to how dangerous a radiation is, okay? Because if we have ionizing of our cells, for example, they've got a really delicate DNA inside them, that can cause mutations and it can cause cancer. But we don't always say that alpha is like the most dangerous type of radiation because actually it's really lowly penetrating. It's not even going to penetrate your skin. So it's unlikely to get into your internal organs and actually cause any damage, really, because it's got really low penetration, it's stopped by paper, and it's only got a range of about 10 centimeters in air. Now, the symbol for alpha, if you're writing a decay equation, is alpha, mass number of 4, proton number of 2. Sometimes it can actually also be written as 4,2 helium, because it can be written as a helium nucleus. And we've got about 10 centimeters in air. Perfect. Right, let's go for beta next. Now, beta is a fast moving electron. So it's got a charge of -1 and it's got a mass of 1/2000, or basically 0, like nearly 0, but it's not quite 0 because it's still an electron. Okay. Now, beta is moderately penetrating. It's stopped by a few centimeters of aluminium. No, millimeters of aluminium either. Or about 1 meter of air. So it's stopped by a few millimeters of aluminium, or it's stopped by a meter of air. It's also moderately ionizing. It's not as ionizing as alpha because it's got a smaller charge and it's smaller and it moves quicker, but it can still ionize other atoms. And the symbol that we use for beta is either beta 0 -1, that's the Greek letter for beta there, or we do E 0 -1 because it is an electron. Now, gamma is a high energy electromagnetic wave. It's got a charge of 0 and it's got a mass of 0 because it's a wave. Now, it's got a really high penetration because it's a wave. So basically, it takes quite a lot to stop it. We need quite a lot of lead or concrete to stop it. In fact, we need a few centimeters of lead or thick concrete to stop it. And it's got an unlimited range in air. Now, it's got a very low ionization, though, because what happens, because it's a wave, it needs to directly strike an electron to ionize an atom. It's got quite a low probability of happening. If we have to write gamma, we normally write it as a symbol like that. Now, the final bit of radiation you need to know about, although we've never really seen it come up in AQA before, is neutron radiation. As the name would describe, it's made up of a neutron. So it's got a charge of 0 and a mass of 1. You don't need to know about the penetration or the ionization, but sometimes it's written as N10 if you're using it in a decay equation. We've not really seen many questions come up about neutron radiation before, but it is in your spec, so it's just worth knowing. But it's neutron radiation made up of a neutron. We can kind of work that out. Right. So, the discovery of the atom. There are 4 main models of the atom that you need to know about. The first one is the plum pudding model, which was discovered by J.J. Thomson. Now, his idea was that the atom was like a kind of spherical, positive kind of dough, and it had these negative electrons just kind of shoved in it, like plums in a plum pudding. Now, these days, we don't really know what a plum pudding is. We don't really eat it very often. So I like to think of this kind of being like a chocolate chip cookie, okay? Your chocolate chips are your negative bits, and the cookie bit is like your positive dough. Now, if J.J. Thomson was correct, and this is what this is what the atom looked like, when we fired alpha particles at very thin gold foil, they should have basically just gone straight through. But they didn't. Some of them rebounded. Some of them rebounded by really large angles, some of them were just deflected by quite small angles. But that gave us this idea that actually, although most of the atom is empty space, because most of the alpha particles went straight through, there actually must be a small positive bit in the middle of the atom, which is where all the mass of the atom is contained, or most of the mass of the atom. So this gave rise to the nuclear model, which was Rutherford. He came up with this idea of the positive nucleus, with electrons around the outside. So we just have our negative electrons kind of around the outside, something like this, okay? Then along came Bohr. Now, Bohr worked out that the electrons had to be in orbit at specific distances around the nucleus. So Bohr came up and had electron orbits, or in chemistry you might call them electron shells. We've got our positive nucleus now, and we've got our electrons arranged in shells around our nucleus. And then finally along came James Chadwick, and he discovered the fact that there are also neutrons inside the nucleus, and that's how we got to our model of the atom that we see today, with the protons and the neutrons inside the nucleus and the electrons orbiting around the outside. So it's important that you know the order in which these stages of the atom were discovered, and that you know the detail of the Rutherford gold-foil scattering experiment. So we had most of the alpha particles went straight through. Which means that most of the atom is empty space. Some alpha particles were deflected. Very few by large angles. That means that we've got a positive mass out the centre of the atom, which we then called the nucleus. Now, the final thing that we need to go over is half-life. So there's a really good definition for half-life, which you have to know, it comes up quite a lot, which is that half-life is the time taken for half of the nuclei in a sample to radioactively decay. Now, the thing that people always miss in this definition is that it's half the nuclei. Half-life is half the nuclei. If we draw it on a graph, it looks something like, if we've got number of nuclei, it looks something like this. So if we're starting with 100 nuclei and I wanted to find the half-life, I'd go down to 50, go along, and then find out what time that would take. So I'd have time in maybe seconds or days or minutes, whatever, or in years going along this x-axis here. So I need to make sure that I just read that axis really carefully, because some isotopes have got half-lives of minutes, some isotopes have got half-lives of millions of years. We just need to make sure we read that axis. Now, we can also talk about half-life in terms of activity. So activity is the number of decays per second. So we time taken for the activity of a sample to halve. The shape of the graph is exactly the same, and we treat it in exactly the same way. The only difference is that instead of number of nuclei here, it will say activity, and we measure that in becquerels. Now, another way they like to ask half-life questions is they like to give you, for example, they might say that we've got 200 milligrams of francium, which has got a half-life of 22 minutes. And then they'll say how much francium will be left after 66 minutes. So this is what you do. First thing you do is find out how many half-lives have passed in 66 minutes. So that'd be 3 half-lives. Then you just need to divide this 200 in half 3 times. So you can either do 200 divided by 2 is 100, divide that by 2 is 50, divide that by 2 is 25. Happy days. Or instead of doing divided by 2, divided by 2, divided by 2, you could just do 200 divided by 2 cubed, and that would also give you 50 milligrams. It's an easy way of doing it. It doesn't matter which way you do it, but it's worth being able to work this out. They really frequently come up in exams, and they're marks that are easy for you to get. Now, the final thing I just want to talk to you about is the difference between contamination and irradiation, okay? So contamination is when a radioactive substance gets in or on an object, okay? So that's like imagining that a radioactive liquid has spilt all over my lab desk and I put my hand in it. Then that thing that's decaying radioactively is on my hand. If I go and touch the doorknob to get out of my lab, I'm going to transfer those particles. If I shake hands with someone, I'm going to transfer those particles. So that is what contamination is. Now, irradiation is just being hit by radiation, or when radiation is incident on you. So that's like, for example, if I walk into a lab where there is a radioactive substance on a desk, I'm going to be receiving some of that radiation, but it's not in or on me. If I walk away from it, I can stop that radiation dose. Or if I put on like lead line shielding or something like that, I can stop that radiation dose. Okay. So a common question is about what type of things can we do to prevent contamination? What type of things can we do to prevent irradiation? So if we're talking about preventing irradiation, we're talking about shielding mainly. Okay. So we're talking about, that's not how you spell shielding. Let's try that again, shall we? There we go. Lovely. So we're talking about making sure that you're putting something between you and the radiation. So we're talking about using, for example, wearing a lead-lined coat, standing behind a lead-lined screen, standing in a different room. If it's alpha, keeping a long distance, using long tongs to keep it away from your body. Those are the kind of things that are going to prevent irradiation. Contamination is prevented by stopping me from touching the object or breathing in the object. So if it's a radioactive gas like radon, I might want to wear breathing equipment. If I need to touch it, I might want to wear gloves or use tongs. It's those kinds of things that are going to stop the substance from getting in or on me. Wearing goggles basically does nothing for both of them, because realistically, if you're wearing goggles, alpha won't get anywhere near your eyes anyway, because it has to be like here to get anywhere near your eyes. Beta and gamma, realistically, they're going to go through plastic goggles anyway, so they're not going to be stopped by safety goggles. This is a really common misconception that we see when we write exam questions, is that we see that students will put safety goggles for contamination or radiation. It's not. If it's a radiation, you want to think about shielding. If it's a contamination, you want to think about how you're going to stop that substance from getting on your skin. And there you go. Those are what I think are the most important points for Paper 1 AQA GCSE. It's not everything. If you want everything, you need to go and check out my resources on the MyEdSpace website. Now, if you want to see more content like this, don't forget to subscribe to this channel and check out all our other videos that we've done. We've done YouTube videos on every single part of GCSE physics. So, I'll see you soon. Take care. Bye.